I've changed my mind. I've decided that there's not enough material for this week, and so we're going to do some examples of this ANOVA stuff now. So let's do some practical examples. So let's go through the structure again of what we're going to do, and then let's work through an example. I think that ultimately that's better for you than leaving it till next week. So let's get on with it, shall we? Okay, ANOVA, what's the central proposition here? My proposition to you is that when the between group variation is large and the within group variation small, it's an indication that there are true differences in the groups. You can do a whole lot of formal math, but I've been thinking about this stuff for years. That's how I think is a good way to understand the ANOVA test. We need to have a Bartlett test to identify whether the variance is equal or unequal. We need to know that because the ANOVA test formula is different. We've got our multiple group comparison. So our ANOVA test is only going to tell us there is at least one difference. It's not going to tell us where that difference is. So the way we're going to do that is we are going to go on and conduct pairwise t-tests, but we're going to apply a correction for the multiple comparison. So the multiple comparison correction is going to moderate the type 1 error. And I've listed a bunch of options. Tukey, honestly significant difference. I use that one a bit too, but the one that I think is really good to get started with is whole, and it's in the t-test function. Okay, so the ANOVA proposition again. What is the ANOVA proposition? Between group variation large, within group variation small, a sign that there are true differences. So that means that we would want to reject the null of no differences. Opposite, between group variation small, within group variation large, that would be a sign that there are not large differences or true differences in the group means, and we would want to not reject the null. So what's the null for this kind of testing? The null is that at least one of the group means is different, and the null is that all the group means are the same, and the alternate is at least one of the group means is different. Now our test, technically, it's the ratio of two numbers. Practical considerations, we're going to use a p-value decision rule to decide which way to go. So remember, this is what between group variation is large, within group variation small. That's going to be the case where we want to reject the null. So you can think about that when we get to some plots that we're familiar with, our box plots and the like. So what are the steps? So the steps are box plot. Why? Because plot is fundamental to coming to understand the knowledge, and it's a fundamental step in our ability to convince the reader of what we're saying. 2, Bartlett test. Why do we do this? Just because we need to know what kind of ANOVA formula to apply. Then we conduct the ANOVA test with equal or unequal variance depending on what the Bartlett test has come up with. Then if we reject the null for the ANOVA test, we go on to the pairwise t-test comparisons with equal or unequal variance, and we will know that we will adequately address the issue of increased type 1 error rate. What are the functions that we need to use? We need to use the Bartlett test function, no problems with that. So if we have p-value for the Bartlett test less than 0.05, we would reject the null that all the group variances are equal. For the ANOVA test, which is implemented via one-way test, so it's one-way ANOVA would be the long name. Again, not too much different from what we know. P-value greater than 0.05, do not reject the null that all the group means are the same. P-value less than 0.05, do reject the null that all the group means are the same, and then try and work out which group means are different via your pairwise t-tests. And if we use the pairwise.t-test function, it automatically controls the type 1 error rate. All right, so let's look at some electricity consumption data. So we've got our different states. So now we're going to consider 4 states. So you can see here, I've read in my data, and you can see now that it says state. State is a factor variable, and there are 4 levels. It's WA, South Australia, Tasmania, and Victoria. Power is my power usage in kilowatt hours, and it's whole numbers. And you can see there are 4,000 observations. It's actually 1,000 observations for each state. So what would be multiple groups? What would be the way that we want to approach a plot for this? We want to approach it with a box plot. So we've got 1,000 observations in each group. Now, if I look at this, I think this distribution is quite a bit smaller than the others, okay? So when I conduct my Bartlett test, which is a test, all of the group variances the same, I'm suspicious, right? I can't be 100% sure that I'm going to reject the null, but this one here makes me a little bit suspicious that it's a bit different to the other three groups. These three, I think, all look pretty much the same. This one, not so much. So we're going to have a measure of, are they all the same, right? So our test is just, if one of them's different, then that's all we need to know to change the formula. So what do we need to do? We need a null. All the group variances are equal. The alternative, all the group variances are not equal. Decision rule, p-value less than 0.05. So in our minds, we've also, the reason this works is because we've actually set alpha at 0.05. That's always what we're doing. I guess I'm starting to treat you like I can take some shortcuts. So we've got a little variation. There are a few ways that you can put this test in. But I've got Bartlett.test power.state. So notice the tilde here. All right, let me back up. All right, look at this. Factor variable 4 levels. So I need to have some notation that is going to pick up the 4 levels of the factor and that these match the values in there. So let me zoom forward again. That's what allows me to do that here. So my response variable here, or the thing that I'm measuring, power, and the factor variable here. So not a comma, a tilde sign. And it's up on the top left-hand part of the keyboard. You'll find it. And then instead of, you can use with, but here it's data equals ozpower. Ozpower is the name of the data file that we've worked in. So this is introducing another way that you can use it. You can use with Bartlett.t-test, or you can use data equals power. All right, so all of that over. Let's have a quick look down here. What do we need to know? Well, all we really need to know is that this guy is much less than 0.05. So that's it. Less than 0.05, reject the null that the variances are equal. So my hunch, based on that plot, turns out to be true. That's not always going to be the case that your hunch turns out to be true. In this case, I've been looking at these plots for a long time, so it turns out I was right, which is, nice, but nothing major. Now, we only did that so that we know which type of ANOVA test to implement is. And we're going to want to implement the one with unequal variance. Why? Because we rejected the null of equal group variances. So the null for my one-way ANOVA test is going to be all the group means are equal. My alternate is going to be at least one of them is different. I don't know which one, or it could be more than one, just one of them is different. My decision rule, p-value less than 0.05, reject the null. So let's have a look at this formula. One-way.test, so that's the test we apply. The measurement, so the power consumption, tilde, so same format as that Bartlett test, tilde state variable, and state's my factor variable, and var.equal equals f for false. And this is the data set to use, data equals ozpower. So you can it says, okay, it's a one-way analysis of means, not assuming equal variance. So that's handy. And what have I got down here? I've got a very strong p-value that is reject the null of non-equal means. Now in this one, I was not so clear that there were differences in the means when I looked at the box plot. It wasn't clear to me that there were going to be differences. The variances I was more certain about, but now I've conducted my formal test, all right? Conducted the ANOVA test. So let's go back and look at that, make sure what we know what we're doing. When we want to conduct an ANOVA test, we're going to use the one-way.test function. What do? We have the response variable or the measurements first. We have the tilde sign, then we have the factor variable. And then the next thing we have to specify depends on the result from our Bartlett test. It's either variance.equal equals true or false. If you reject the Bartlett test, you put the false there. Data, what data set to use. So this is quite, if you were trying to do this kind of stuff in Excel, crazy time. In R, no problems at all. So we've gone on and we've rejected the null. Now, what have we got? Oh my goodness, these are all of the comparisons that we could do. So we can compare Victoria and Tasmania, and so on, and so on, and so on. So later on, we will look at some different ways of expressing all of these, but we have 4 groups. So when we have 4 groups, we have 6 possible combinations. And the great thing for us is that we're going to be able to do all 6 combinations with the stroke of one command. So we're going to type in one function and it's going to give us the output. So let's do that. So it is switched back notation here. So with the OzPower data set, apply the pairwise.ttest function. Slightly again, different notation here. I've got power, comma, my factor variable state, pool.st equals false. F or false, okay? So I'm lazy. Capital F or capital T works for true, false. I've written it out fully here. So what have we got here? With the data set, OzPower, apply the pairwise t-test function where the measurements are power and the factor variable is state. And because I rejected the null for the Bartlett test, set the pooled.standard deviation equals false. Now let's look at our results. So our results come out in this table, and you can see down here it tells us that we have automatically applied the Holm adjustment. So that's pretty handy for us to know. So let's see how we read this table. So it says Tasmania compared with South Australia, p-value less than 0.05, reject the null. South Australia compared with Victoria, reject the null. South Australia compared to WA, do not reject the null. Tasmania compared to Victoria, do not reject the null. Tasmania compared to WA, reject the null. And WA compared to Victoria, reject the null. So, later on we would go and look at in detail about some of the more practical things about what we subsequently do with this data. But what we've been able to do here is apply one line, so one function, and it's conducted all of the t-tests for us. So it's conducted 6 t-tests for us, and it's also introduced the an adjustment to control the type 1 error rate. So that's pretty handy for us. So what have we done? So it's p-values table. It's right, nice and easy for us. So what have we done? When we have ANOVA, we have many, and please don't do that. We have a formulation that we follow, box plot, followed by Bartlett test, followed by one-way ANOVA test, followed by multiple t-tests if we reject the null for the ANOVA test. And then we draw some conclusions. So I'm not really focusing on drawing the conclusions at this stage, really focusing on making sure that you understand how to conduct the tests. So let's look at what do we use. What are the functions in R that we use? We use the Bartlett test to test for constant variance. We use the one-way dot test to establish whether to conduct the ANOVA test. And then we use the pairwise dot t test to automate all our routines for the multiple comparisons. All right, so let's have another look at an example. So when we had our PM 2.5 data, this time I've got 3 groups. So if I had 2 groups, we saw how to conduct this. 3 groups, you can see it is 3 levels here. And if I've lost my clicker again, I don't know what's happening with my clicker. 3 groups, come on, there it is. So we've got a factor variable, which is the suburb, in there south, north, and central. We've got 2,911 observations. The PM measurements in the PM column. So I've read my data into R. We're pretty confident doing this now at read.cv. So what did I do first? I set my working directory. I downloaded my data file. I then typed the object name that I want to work with in R, read.csv, and then read in the data file name from where I've saved it. And so now I've got the object PM25 to work with. I have a look at it using the structure command. Tells me I've got data frame. These are the things that I've got. First step, box plot. What does it look like? All right, well, we see in the central, like this streaming off here. So that makes me worry about the variances. I think that this level of dispersion is going to mean that they're the same. And actually, I'm looking at these and I'm thinking, gee, I don't really see that there's a lot of differences here. But I think that these variances are going to be different. So, this is the kind of practice that you get looking at data. So let's go on to our first step. Our first step is going to be to establish the Bartlett test. So my null, all the group variances are equal. My alternate, the group variances are not all equal. P-value decision rule. How do we go down here? Bartlett test, PM. PM is our PM 2.5 measurements. Tilde, the factor variable suburbs. Bartlett test of homogeneity of variances. So homogeneity. P-value, what is the P-value? It's less than 0.05. So I reject the null that the variances are all the same. So I'm going to conduct an ANOVA test. Again, my ANOVA test is going to be with unequal variance. All right, so let's set up the null. The null is all the group means are equal. The alternate is at least one group mean is different. P-value less than 0.05, reject the null. All right, again, let's look at the structure here. One-way.test, PM, tilde, factor variable suburb, bar.equal equals F for false. You can see I'm lazy. Data PM25. So that's the data object I read in. This is set to false because we failed the Bartlett test. And this is the structure. You know, it's the variables, the numbers, and then the factor variable. And that's the function that we're applying. And we get our nice report down here. It's a one-way analysis of means, not assuming equal variance. And I look at my p-value, and my p-value is above 0.05. So I do not reject the null that all the group means are the same. There is no evidence, or there's insufficient evidence to conclude that there are differences in air quality across different parts of the city. Important point. You do not now do t-tests. Okay, so the ANOVA test is more powerful than our t-test. So our more powerful test has failed to detect any differences. Therefore, we stop the analysis. You do not go on to multiple comparisons, right? Now, I'm saying that very clearly because I'm about to go on and do multiple comparisons just to show you. But to be clear, when you do not reject the null, you do not go on and do multiple comparisons. Okay, so if hypothetical, well, we didn't do this, but just to show you what happens, but you're never going to do this yourself because it would be the wrong thing to do, would be to go on and conduct the t-tests here. Now, what you can see that's happened is when you adjust this, it's made all the p-values 1. Okay, so there's clearly no differences that we're going to find. But you don't do this. Cross. Never do this. All right, so I'm going to squeeze in one more example here. So I've got the sulfur dioxide levels from China, 3 levels for my factor variables, central, north, and south. Read in my data, have a bit of a look at it, see that I've got factor variables, I've got 1,000 observations for each location. Is the sulfur dioxide level different across the regions? Again, I'm not going into the interpretation of this kind of the results, which is really what we want to get into. I'm going through like the boot camp exercise of how you conduct this type of analysis. So first step, box plot. All right, what am I learning from this box plot? Again, I think that maybe this one's more spread out, but I think that this south one looks different in the mean, like the distribution looks a bit lower, so maybe emissions are lower in the south. Not sure about these guys, but I also think that this spread looks a bit different to the other two. So here I'm thinking there might be some differences. Not sure. Let's go on and see what we get. So Bartlett test, again, ANOVA test comes up, unequal variance. So we, same thing, group variances are equal, group variances are not equal, rejection decision. Look at our structure, Bartlett test, SO2 measurements, tilde, region, data, China SO2. What have I got? I've got the results for a Bartlett test of group variance homogeneity. P-value is less than 0.05. Therefore, I reject the null. Variances are not all equal. Conduct my ANOVA test with unequal variance. How do I do that? Set up the null. All the group means are equal. Set up the alternate. At least one group mean is different. P-value decision rule. If the p-value is less than 0.05, reject the null that all the group means are the same. Now remember, why am I applying this p-value rule of 0.05? That's because I've set my alpha level at 0.05. So I'm being a bit lazy with that, so you know that it's always alpha 0.05. So you need to structurally, you need to set that when you talk about your tests. One-way.test, SO2, tilde region, bar dot equal F. Okay, so because of our Bartlett test results, we're getting the hang of this. We look at our p-value, we reject the null that all the group means are different. There's at least one difference, so we need to progress and see if we can find that one difference. How do we find that one difference? Well, we use our pairwise t-test function with our controlling the type 1 error rate setting. So these are the three tests that we can have. North is equal to central, north is equal to south, central is equal to south. So when we're talking about t-tests, so we're talking about differences in the mean. So, and we have, again, set for our t-test an alpha level of 0.05, which means that if we have a p-value of less than 0.05, we're going to reject the null. And because we use the pairwise .t-test function, we can safely use the p-value 0.05 rule because it has adjusted the p-values that it reports for the multiple comparisons issue. So what are our results? So let's have a look at our results. So with our China SO2 dataset, apply the pairwise.t-test function to we put the measurements here. So these are the SO2 measurements, put the factor variable next, pooled.standard deviation equals false. Why do we have that? We have that because we rejected the null for the Bartlett test, so it's not using the pooled variance. And it turns out that they're all different. So they're all different. So the central north comparison, p-value less than 0.05. The central south comparison, p-value less than 0.05. The north-south comparison, p-value less than 0.5. And that is all taking into account the possibility of the type 1 error rate being inflated because it's applied the Holm adjustment. So that's the end of the examples. I think that this time genuinely it's enough for this week. You've seen the motivation for the ANOVA test. You've seen why we have problems we have to control for the type 1 error rate. And you've seen a couple of examples of the structure of conducting multiple comparison tests. And that's not a bad effort for the week.